Well, let's attack the numerical solution of that matching condition that we got in the previous video. Remember, we were looking for the wave functions of this form, the even solutions, and that led us to match these at x equal to a, led us to this condition where k and alpha were defined as shown. And to solve that equation numerically, uh, one has to have specific values for the parameters, namely for A, for M, and for V naught, specific numerical values. And then one can look at this if you solve this for K and plug it in up here and here, and solve this for alpha and put it up here, then this becomes an equation that really only has E as a variable, and so this one could, at least in principle, solve this equation one for the energy levels. Unfortunately, you can't do that analytically in closed form, so we have to use a numerical method to do that process. And to do that, I'll manipulate equation one uh, in a fashion that is beneficial to doing the analysis, the numerical analysis. First thing to note, I can distribute across equation 2a, the 2m over h bar squared across both of these terms. And then just note that this term here, 2me over h bar, is the same as this. And so I could replace this with simply minus alpha squared and then solve that for alpha. Alpha squared is this, and then alpha is the square root of that. And then the next thing to note is I want to get this in dimensionless form. It's usually always better when you're doing any kind of numerical work to cast all of your equations in dimensionless form, and we'll do that here. And we're kind of led to how to do that by the argument of this tangent. Any argument of a function, like a sine or cosine or exponential, or really any function, has to be dimensionless. Okay. So this needs to be dimensionless. And in fact, if you look at the units on it, k has units of reciprocal length, a has units of length, and so when you multiply length times reciprocal length, you get those two cancel, and so it becomes dimensionless. So we're led to introduce the dimensionless variable z, and I'm just defining z to be k times a. So that's really the equation from equation 1 up above. And now then we plug that in. Ka is just z, and everything else I stayed the same here. The only difference is equation 1 alpha. I used this relation, took the square root of both sides to replace alpha by this square root. And then, since I know Ka is dimensionless, so then I'm sort of led to multiply this equation by A. So that I get Ka here, which I know is just Z. And then when I multiply this side by A as well and bring it inside, I get these two. And then I get Ka squared here, which again is just Z. So altogether, I get it into this form here with Z equal to Ka or Ak. And you'll notice that this parameter here is all things that I'm assuming we know the numerical values of. M, the mass of the particle is trapped in the well, V naught is the depth of the well, and A is the half width of the well. So this, for a given potential well, is just some dimensionless constant. Again, you can check this, but it is indeed dimensionless. And so I define z naught to be just that, well, really the square root of this constant is also dimensionless. So I define z naught to be that so that I could represent this as z naught squared. And now I've got everything in dimensionless form. And in principle, I could plot that, except I don't really know how to plot z times the tangent of z. That's not a function that I'm real familiar with. So I divided both sides by z. And that gets rid of it over here, leaves a tangent on this side. 1 over z I take inside, and so I get a z naught over z squared, and then z squared over z squared is just a 1. So I evaluate 1 one time for a given potential well, I evaluate what that really the potential well constant Z naught is to a numerical value, and then I've got an equation just in Z, assuming I know that the number Z naught is, and I can solve it numerically. Now you can use really any numerical technique that you're familiar with. So you might use Newton's method or Newton-Raphson, and there's some other techniques, just simple iteration, etc. But it's always better in doing numerical analysis to use some graphical guides to help you out. And that's the reason for this manipulation into this form. Because I know how to plot the tangent of z. Here's the z-axis. I'll plot the tangent of z. And I know what those look like. They have asymptotes at all the odd values of pi over 2. Pi over 2, 3 pi over 2, 5 pi, 7 pi, etc. And so I know those curves, those little S-type curves. And this other one I can plot pretty easily as well, in that I know when z is 0, 0 into this, it's going to be infinite. So it's going to shoot up very rapidly to infinity, and then it drops. It's going to continue dropping as z gets bigger. This number gets smaller, and so this whole thing gets smaller. But at some point, I'll get some value of z, namely when z is equal to z naught, that this becomes 1, and so this right-hand side, the square root function, will go to 0, and that's this point here. So that square root function is going to look something like this, at least in this sort of typical example. Now, depending on the value of z naught, it could be very, very close over here, or z naught could be way out there in 3,000 or 4,000 values. But this is a fairly typical looking thing. It's going to all look like this. Notice now then I can get the solutions to this by where these two have the same value. Any value of z where the tangent and the square root function are equal, those two curves will cross. So here the tangent, here's the square root function. Where they cross, is a value of z in which they both have precisely the same value. So every crossing, I can come down right below it and get the z1 in this case, because it's the first crossing. And if I plug that value of z1 here and that value of z1 here, that these two sides would be equal, and I would z1 then is a root of this equation 3. Next crossing is out here, and that's where the two are equal. You come right below it, you get the second value z2 that plugs in here. The next one, a crossing, is here. That value is z3, and that would make these equal as well. In this case, there's only 4 roots, so you learn a solid piece of information there. So you can count, once you've done this, you can count the number of roots. And then it also gives you some guidance on using the numerical method. So if I were going to use really a MATLAB or Mathematica or any other software to find the roots of that equation, they all want you to provide an initial guess. And so if I want this root here, I'm going to give it an initial guess somewhere down in this region, and then it'll converge pretty rapidly to this z1. I wouldn't give it a initial guess over here, because it'll never get past this this place where the tangent function becomes infinite, basically. What it will do, if I give an initial guess over here, it's going to converge to this other one. So you get some guidance on initial guesses to guess for the numerical technique to find the root that you want in any given region. Well, once we have those located roots, z1, z2, and z3, then pretty obviously, if I plug in z1 into this equation, A, I assume, is known, and I can get K1. So Z1 will give me K1. I'm going to call it K0 here for reasons we'll see in a second. Once I've got K0 corresponding to Z1, I can come up to one of these other equations. probably here. I can plug that value of K naught in here. It'd be a numerical value. And I would know everything in this equation except for E, and so I could solve for E, which I denoted as E naught. So now I've got E naught, and then I can get the alpha value. Once I've got E naught, I come to this equation. So I've gotten from K naught, I get E naught. From E naught, I plug that here and get alpha naught. And I do that for each one of these roots. The next one, Z2, I label that E2, K2, and alpha 2. And then the third one up here, I label that E4, K4, and alpha 4. So I have three roots, but I label these with even values because, as we'll see, they will give us even functions, eigenfunctions. And then I've got all those values, so I know E naught now. That was the value that we got here. I can get psi 0, that's the eigenfunction associated with this eigenvalue. I just plug in my K naught and alpha naught to go in here. So I get the wave function psi 0 that corresponds to this eigenvalue. Likewise for E2, once I've got E2, I've got K2 and alpha 2, so plug those numerical values in and do likewise. And for 4, I get its eigen function associated with E4. A couple of things to note. In this case, just as by way of example, I've only got 4 roots, but you could have 20 or 30 or several hundred, depending on the precise values of M, V naught, and A. However, there are a few limiting cases that can help you out some. It turns out if Z naught is large, and so Z naught is going to be large. If V naught is large, that means the potential well is very deep. And if A is large, which means it's very wide. So for very wide, deep wells, Z naught is large. And if Z naught is large, it's going to be way out along these axes, and these crossing functions are going to be very, very close to the asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. So in that case, I know that the Z ends, that's where they would cross, are very close to n pi over 2, where n is 1, 3, 5, 7, all the odd numbers. Once I have those, I can find the k-ends. That's just going to be 1 over a times the n pi over 2. And then once I've got the k-ends, I can solve for the energy levels, which I've done here. Again, where n is 1, 3, 5, etc. So I get the energy levels. On the other hand, if V naught A and A are small, it's a very shallow well and it's very narrow, some combination, then Z naught's going to be small. It could be so small that it's down in this range, so it comes down and drops. It never comes out enough to hit this even the second one. But you'll notice, because of the shape of this tangent function and the shape of this function, I'm always going to have one crossing, and so I'll get one Z, Z1 that will satisfy it. So we have that case. We'll always have one even solution. May have more. We might want to get some estimate of how many energy levels we might have, and it turns out you can use the infinite potential well to get an estimate on the number of or the maximum number of n that or energy levels that you'll have. If you remember, for the infinite square well, we had h bar squared over 2m, n squared over the width squared, which I'm represented as L here because we've got this factor of 2 that's a little bit different. We used the total width, and A now is the half width. And that you can solve for the case. I know that En in the bound state problem in magnitude has to be less than V naught. And so I can use that information to find that the maximum value is the value here. So if I know m v naught a and well I got h bar, then I can get at least an estimate of what the maximum value is. Will be the square root function on this side.